Well, the sun is supposed to be close, and the sun is supposed. So what they say is they don't know what it is. I've heard that said by quite a number of them, including Dell and others. Well, you know, it's a luminary, and we don't know what it is. The truth is, you don't know what it is. I do. And so do all my colleagues, and so do most people who've been to school for any time. And we know that, what it is, for a number of reasons. First of all, we have instruments. We have spectroscopy. Just hang on a second, I've got to fix the battery on this thing. Okay, there we go. All right, so where was I? Okay, I said we have spectroscopy. All right, so what is this? Well, one of the things that we get from the sun is visible light, the visible light spectrum. Okay, that starts from red all the way to red, RGB, so red, orange, yellow, green, blue, indigo, violet. Okay, that's the visible spectrum. It's all radiation. The radiation all the way from kilometers in wavelength to nanometers in wavelength. All of this is radiation. It's all the same stuff, photons. Okay, it's just that as humans, we can only see a small range of it. We can only see the visible light spectrum, the part that's the wavelength between red and violet. That's all we can see. Okay, you can see colors. You can see that the colors on this board here, I've got the red writing over there, and the reason that it looks red to you is because it's reflecting the red wavelength and absorbing the rest of it. The reason why the board is white is because it's absorbing it's reflecting all of the wavelengths, absorbing none of it. The reason that the blue is there is because it reflects the blue and absorbs all the other colors. Now, did I misspeak on the red? It reflects the red and absorbs all the other colors. Okay, so whatever color you see, that's what's getting reflected. Okay, so this is the visible light spectrum. This is what you see. Now, the amazing thing is what's been discovered looking at the spectrum through an instrument called a spectrometer, is that each different element produces this visible light spectrum with specific lines around it. So there's small lines, dark lines that go through, that cut through this spectrum. So you can see the spectrum looks like a rainbow. So imagine the rainbow cut with dark lines in various places. Okay? All right? These are called spectral lines. Now, the thing is that each element has a different spectral line, a different set of spectral lines. Okay? They're in slightly different places. This means we can use that information about what these spectral lines are to determine what the element is. Okay, now it's complicated to explain how this happens, but suffice to say, as energy is released, this energy that you see that comes through to us as this in the visible light spectrum, as energy is released and all things get back to their normal state, they release the energy. Now, it's a result of this that we get to see the spectral lines. If you want a a physics lesson on how spectral lines happen. I'm happy to do that, and if you want that, just put that in the comments, and I'll do a lecture on spectroscopy. We can look at the whole thing and how that works. So go ahead, I'm happy to do that. But for this particular video, I'm telling you that the elements have unique spectral lines, so you can tell which one is which, just looking at that. So you get your spectrometer, you look at it at the sun, and it gives you the electromagnetic spectrum, and you can see the spectral lines, and then you can compare them to all the spectral lines for all of the elements on the periodic table. And you can do that yourself, by the way. These spectrometers are pretty inexpensive pieces of equipment. You can actually buy one yourself, and then you can look at it and then compare it to the periodic table. And guess what you'll see? You'll see the spectral lines for helium and hydrogen. No others. You'll see helium and hydrogen. Now, when you look at that, the other thing about it is you can also tell the abundance of it. When you look at that, then you know what the sun is made of. And you can see that it's helium and hydrogen. Why is it hot? Why is it like this ball of huge amount of energy? It's because there's a fusion reaction happening here. It's a plasma, the sun is a plasma with a huge fusion reaction happening between hydrogen and helium. How do we know this? Because those spectral lines tell us that. Not only do the spectral lines tell us that, but the sun gives off other radiation. So it's not just the visible light. So other predictable things come from the sun because we know what it is. The heat. We expect to get the heat because of a fusion reaction. We can actually produce small-scale fusion reactions, and we know that it's going to give us the heat. So we can expect the heat. It's exactly what we do expect for the amount of mass that there is. Remember the mass? We worked it out up here. Okay. Then, what other radiation do we get that the sun gives off? X-rays, gamma rays, in fact the whole suite of the entire electromagnetic spectrum comes from the sun. Okay, so radiation. What have I written over there? Right, the spectral lines. Okay, just on a matter of note, not that it has anything to do with the sun per se, but there's X-rays and gamma rays. They are dangerous to us. There wouldn't be any life on Earth if the sun was only 7 kilometers away and we had to put up with all of this radiation. Because there's nothing that stops this radiation from getting to us. Have you heard of irradiation? This is where you disinfect something using irradiation. This is done using gamma rays. Okay? It's guaranteed to kill all the bugs. It's guaranteed to kill anything that's alive. So we irradiate stuff. Well, the sun gives us that irradiating radiation. So, what would happen to us if we had no way of stopping those gamma rays or those X-rays? What do you think would happen to us? Well, it happens to people all the time who get exposed to this. They get cancer. Okay? The chances of surviving cancer from a dose of radiation that gives it to you is pretty well next to none. Do we use radiation like that to even kill cancer because they can pinpoint exactly where it is, where the tumor is, and use this radiation to kill the tumor? So you can see what radiation does to tissue. There's many instances of those people when the bomb landed at Hiroshima and Nagasaki. Those people that had radiation burns. Okay, it's really damaging stuff. Well, if the sun was 7 kilometers away, how would we stop that from happening to us? When are you going to think about that? Okay, all right, so how does that happen? When it's 93 million miles away, or 1.49 by 10 to the 9 meters? Well, good for us. We have a magnetic field around the Earth. And what that magnetic field does is it deflects this stuff. So we don't get any of that. Okay? This magnetic field stretches a long, long way. So if the next thing you're going to say is, why doesn't it affect the people on the International Space Station? Well, of course, they've got to be concerned about cosmic rays. They have to have shielding from that. They don't have to worry about alpha particles, like the Van Allen belt, because that can't even go through paper. So we say, oh, how did they get through the Van Allen belt? Well, you know, like they did have more than paper, right? And then they knew about the Van Allen belt in the 50s, so they were able to get to take a trajectory through past the poles to get past it. Okay, you know, you could just look this stuff up yourself. Okay, next. All right, so what I said, the magnetic field. Oh, by the way, I'll make a video on this magnetic field too, because there's a few things that are misspoken about that in your Globe Light tour and other proselytizing nonsense. But we'll have a video on that. We'll talk about what magnetism is and electromagnetism, because that is so badly misspoken that you know that word is so badly used, electromagnetism, that I think that deserves a special video just to talk about that, and we'll get on to that. Okay, all right, so the next thing is the velocity of the sun. I just wonder how much thought you actually gave that. So, if the Earth is flat, then whether you think there's a model or not, it's got to cross your mind that the sun is there, and you saying, well, like Dell says, or some of the others, it's demonstrably a plane. That's what they say. It's demonstrably a plane. Globe lie. Well, we don't know what it is, but it's not a globe. That in itself is a really dumb statement to make. Okay, and it's not usual for an educator to say that that something like that is dumb, but this is. Okay, you can't say I don't know what it is, but it's not this. Okay, so the velocity. If you accept that it's demonstrably a plane, then you've got to accept that the sun gets around the plane. Okay, so unless you think it's one great big stretched out piece of land, you know, with an edge either side, you know, like a rectangle, maybe that's what you're thinking. And then I don't know, how does the sun get around? Go underneath it, then back again? Whichever way you do it, it's fraught with problems. And you only have to think for a minute to figure out those problems. One of those on this will be the velocity of the sun. We see the sun travel at the same rate as you people in the north. Okay, when I say we, I'm an Australian, if you haven't figured that out. At the moment I'm in India, so I'm sort of halfway up there. I'm in the northern hemisphere. Okay. Now, we see the sun travel at the same rate. It doesn't travel any quicker if you're in Australia. I've had actually somebody like Zoom Truth and Marilyn actually say tell people in America, you know what? Australians see the sun go faster. The sun goes faster in the southern hemisphere. That's just a flat out lie. And the people who say this didn't even think for 1 second. See, in the time zone, us in Australia, those people in Southeast Asia, in parts of Southeast Asia, and those people in Russia, we all see the sun at the same time. The sun moves at the same time for all of us. We're all in the same time zone. When it's 6 o'clock for us, it's 6 o'clock for them. So, how is it going faster for us and slower for them at the same time? Why are you not asking yourself that question if you care that what you believe is true? Because clearly you're not asking that question. Because it just doesn't work. And it doesn't take any superior mind to figure that out. How come the people in Russia and us see the same sun going at the same rate if the sun around our part of the world would have to travel 3 times faster than the people in Russia? I'd like Brian's logic to think about that. I did a video on Brian's logic. He never spoke about it again after that. Well, all of you who think Brian's logic is logical, think about what I've just said. Now, if that's a problem for you, and it should be, then you need to reassess what you think about what the sun is, because this video is about the sun. Okay? It definitely cannot be going around on a flat plane and be the sun that we observe.